Okay. Okay, Muhammad. Today, inshallah, we'll finish the astrophysics. We have the last concept, uh, four main points. They are talking about Hubble's law and something called the Doppler effect, and how Hubble used the Doppler effect and redshift as an evidence for the Big Bang theory. So it is very, very important. But first of all, we have to revise a very small part. I think you know it. It is the emission spectrum. If you remember in emission spectrum, we say that the atom which have discrete energy levels, the electrons started to be excited. So they are moving from the lower energy levels to the higher energy levels. Then, when they are dropped down, a specific photon equivalent to the energy is emitted, right?
Yes.
So, great. So again, if we have electron, and this electron drop down from higher energy level to lower energy level. So a specific photon of energy equivalent to each frequency will emit it. And we said that there is a relation between the energy and the frequency, which is directly proportional. What I mean, as energy increases, how energy increases? When the difference between the two energy levels, the higher one and the lower one. I mean that if we have 4 electrons that are located in energy 4 level and the energy 3rd level and energy 2nd level, and they are down. So the maximum energy will be for the electron which fall down from the 4th energy level to the ground. So as energy increases by increasing the difference between the two energy levels, what will happen? The frequency of emitted spectrum will increase, which make the wavelengths to
increase.
Right. But I mean that each electron drop down will emitted in the form of a specific photon. This specific photon has a certain frequency. This certain frequency meets a certain wavelength. Great. So, if we have four energy level like this, 1, 2, 3, and 4, and we have this electron, and this electron, and this electron. We don't have another color, so instead we will use this one. Okay. So they are located in different energy level, E4, E3, E2, E1. Then this is a ground state. When the electron found in the highest energy level started to drop down, it will result into a spectrum. We called it emission spectrum, right? This spectrum have the highest frequency ever, which have the shortest wavelengths ever, which is approximately B, appeared in the form of blue colors. And we called it a characteristic emission spectrum light, if you remember. And if this electron in energy 3 started to drop down, what will happen? It will emit a photon. This photon will have a certain frequency, which approximately in the green region. While if this one drop down, which is the red, so it will emit the lowest energy, by mean the lowest energy level, by mean the longest wavelength, which is red. So we call these colors are characteristic emission spectrum. And this characteristic, so this blue, which have highest energy, energy max, E max. This is red, which have energy minimum. So by knowing this spectrum, we can define the element itself. By mean that this characteristic, and the word characteristic, it means that it looks like a fingerprint. So each element has its own characteristic emission spectrum. So from this spectrum, we can determine the type of the element and we can define the atom itself. So this one, we call it characteristic spectrum. Do I mean that? If you start to receive some spectrum from an element and you found that its emission spectrum was in the form of sum of lines. What's the meaning of this one? We said before that if we have a complete or continuous spectrum, and this has happened for the sun or for the huge stars, because the stars are very dense, which contain an infinite number of electrons in all energy levels, which permit the electrons to fall down from energy levels and emit different frequencies and all the wavelengths. So we call it continuous spectrum. But if this continuous spectrum absorbed by some elements, what will happen? You will find the absorbed spectrum in the form of dark lines. And these dark lines, we call it the characteristic spectrum, from which we can know exactly the element contains inside this body. By other means, if you have a star, a huge star, The star is a very dense object which have all the possible electrons in all energy levels. So it looks like a source for continuous spectrum. I mean that if we are here at Earth accepting the spectrum which got from the star, you will see that the spectrum is a continuous. But unfortunately, not all the spectrum reaches to us. Why? Because outside the star, we can find that there is a layer of dust. Do you remember this question? Yeah. This dust is less dense, which contains some atoms. So what will happen? The atoms located inside this dust layer will start to absorb some of the spectrum and re-emitted it. So the spectrum which reaches to the Earth will not be a continuous spectrum, it will be absorption spectrum. Because if this atom absorbs it, some of the spectrum as blue or red or green, so it will be appears in the form of dark lines. Hubble used this spectrum which getting out from the star. And by studying this spectrum, he found that this characteristic spectrum looks like the spectrum of carbon and helium. So he makes sure that the stars containing two elements which are carbon and helium, and these atoms of helium and carbon are found in the less dense layer around the star. Again, the beginning of Hubble is when he noticed that the spectrum which comes from the sun or the star towards us is not a continuous spectrum. Why? Because between the star or the sun and the earth, there is some atoms, there is no space. So this atom absorbed some of the spectrum and re-emitted it. So the spectrum reaches to us with a dark lines or a characteristic spectrum. We define the characteristic spectrum as it is the spectrum which emitted when the electron is dropped from higher energy level to lower energy level. And this characteristic line spectrum is considered as a fingerprint, and from it we can know exactly the time of element and atom. So by studying the spectrum which getting out from these stars, he recognized that all the stars which are very dense objects are surrounded by a layer of dust. This dust contains mainly of helium and carbon. But this is not important. The important thing is that he found that these lines or dark lines are shifted. What the meaning of shifted? Let's see. But before, any doubt about this introduction?
No, sir.
Okay, great. So, Hubble law. This is the beginning of the chapter, or this point on the chapter. Hubble studied the absorption spectrum spectrum, which reaches from stars toward the Earth by a telescope. He found that this is the dark lines, but when this dark lines reaches to the Earth, he found that these dark lines or characteristic lines are shifted. So there is a difference happened in distance. So he asked himself, why these characteristic lines started to be shifted? And he remembered Doppler effect. Do you remember Doppler effect?
Yeah.
Yeah. If we have a source which emits any wave, and we have two observers, so if the source is constant, so both wavelengths and the frequency on both sides will be the same. So lambda 1 for the first observer is equal to lambda 2 for the second observer, and the frequency the same. But when this source started to move towards an object, they found that the wavelengths due to the second observer, or the observer which is located further than the object, increases. And the frequency decreases. So Hubble started to ask himself, what happened exactly for these characteristic lines? Because as it shifted, it means that its distance increases, by mean that its wavelength increases. And as the wavelength increases, it means that it turned from a color into another color. By mean what? By mean if we have this galaxy,
Yeah.
and this galaxy containing the source of light and the telescope that we will detect the light from it. So if the two objects are constant and they are moving, not moving away from each other or closer to each other, so if this light emits a wavelength, emitted wavelengths, so it must reach the same. But when Hubble found that there is a shifting happened, by mean that there is a change happened in wavelengths, it means that something happened here. And this something means that one of the two objects started to move away from the other. Of course, it will not be that telescope. The telescope is constant, fixed. So it means that the star started to move away. And as the star moving away from the telescope, its wavelengths will
increase.
So instead of reaching a wavelength in a certain color as blue, you will find that it started to turn into red. And this is what we called red shifted. What the meaning of red shifted? It means that the wavelength changed from a value to another value, to another larger value. From another color to the red color, because the red color is the longest wavelength ever. And this is an evidence that the star or the object which emit the light is moving away from us. So Hubble started to put a relation. And he started to say that the distance between the emitted wavelengths and the observed wavelengths, we will call it scale factor. And he gave it a simple A. And this is another scale factor. What happened for the scale factor? It increases, right?
So your scale factor distance between the telescope and
the emitted and the observed.
That means the star and the telescope? Or?
Yeah, the Earth and the star. A body observed the light which comes from an emitted source. So it means that a stretching happened, right?
Yeah.
This stretching happened is equivalent to the difference in wavelengths, right? Or the change in wavelengths. But I mean that if we said that A2 over A1, by mean that the scale factor that we observed over the scale factor that emitted, by mean that if we waiting for a certain wavelength which come, so this is a distance, or this is a scale factor which we waiting for. But what we observed was different. We observed more scalar factor or larger scalar factor. So he found that the ratio between the second scalar factor, which is the observed scalar factor, divided by the first scalar factor, which is the emitted scalar factor, is equivalent to the ratio between the wavelengths observed and the wavelengths emitted, right?
Yeah.
Great. And here you recognize another thing, which is the percentage of redshifting. What is the percentage of the redshifting? By mean that if this wave is moving with the speed of light, so what happened when the wavelength increases?
It increases.
Great. So Hubble reached to an important relation. The relation between the distance that the star started to move further from another object and its velocity. And he called this velocity recession velocity. And he gave it a sample V, or the straight-shed velocity. So recession velocity by mean a straight-shed velocity. And he said that the ratio between this recession velocity over the speed of light, or the normal speed of light, is equivalent to the change happened in wavelengths divided by the original wavelengths. Again, Z for Hubble, he called it the redshift percentage. Shift percentage. And he said that the ratio between this velocity, what is this velocity? Recession velocity, or the straight-shed velocity. Or the velocity by which the star moving away from us. And this is the speed of light. Is equivalent to what? What made this velocity?
Change in wavelength.
The change in wavelengths, right?
Yeah.
So delta lambda over lambda E. And this delta lambda is equivalent to lambda observed minus lambda emitted, right?
Yeah.
Great. So he found that there is a relation between the recession velocity and the speed of light, which is equivalent to delta lambda, or the change happened in the wavelengths, over the emitted wavelengths.
مش اللامدا observed أقل من اللامدا emitted.
أكبر. We observe it after being shifted.
Okay.
So it is in the red color. It is red shifted, but I mean that the wavelengths become longer.
Okay.
Right? So by multiplying by C, we can find that V is equivalent to, both sides we will multiply it by C. V is equivalent to delta lambda over lambda multiplied by C. And this is the relation from which we can find the recession velocity. Sorry. So this is the recession velocity. So again, simply, Hubble's studied the absorption spectrum which come from a star. And he found that there is a shifting happened in the line spectrum. What I mean that, and instead of being in their proper positions, they are shifted by a distance. This distance considered it as delta lambda. And he asked himself, what happens in order to make this shifting? Of course, it is about Doppler shift or Doppler effect. And as the wavelength increases, it means that a body moves away from another body. Which one? Of course, the source of the light. So if we have a source of light, or by other means, a star found in a galaxy, and an Earth or a planet or a telescope which observe the light which comes from it, instead of accepting the real wavelengths, it will be longer. And all the wavelengths which come from these stars are redshifted, by mean that it shifted to the red color, by mean that their wavelengths increases, which means that the star is moving further away from us. And this motion is called a recession velocity. And in order to find the value of the recession velocity, he said that the distance between the observed wavelengths and the emitted wavelengths is called the scale factor. And the ratio between the scale factor observed and the scale factor emitted is equivalent to the ratio between the wavelengths observed and the wavelengths emitted, which give us another meaning, which is called a redshift percentage. This redshift percentage is how much the star and the planet are moving away from each other. Or by other means, if the right hand is the star and the left hand is the Earth, so how much your hands stretched away from each other. So this stretching will happen by a certain velocity. This certain velocity compared by the speed of the light is equivalent to the changing happened in wavelengths between the observed and the emitted wavelengths divided by the emitted wavelengths or the original wavelengths. And he defined the recession velocity as it is a velocity of a star which is moving further from a constant body. And the mathematical relation for this recession velocity is delta lambda divided by lambda multiplied by c. Delta lambda by mean the change in wavelengths, which is equivalent to the observed wavelengths minus the emitted wavelengths over the emitted wavelengths multiplied by c. There is a very, very important condition that always v is much lower than c. So the recessional velocity, as it increases, but it cannot reach it to the speed of light.
Okay.
Great. After that, he started to draw a relation combining between the recession velocity, or by other means, the redshifting and the distance between the star and the constant body. And he found this relation. He drew a relation combining between recession velocity and the distance and for your information, the distance between the stars is measured by a unit called parsec, PC, parsec. Each one parsec is equivalent to 3.1 into 10 to the power 16 meter.
Okay.
So this is a very, very, very large distance. And if you converted it into light years, so we have to divide by 9.5 into 10 power 15, you will find it is approximately. Can you calculate it for me?
Yeah. 3.1 into 16 divided by 9.5. That's 3.26.
Okay, so 3.26 light years. And he measured this distance with megaparsec. So this one becomes 22. So 1 megaparsec as a distance between two stars or a distance between the stars inside any galaxy is measured by a unit of parsec or megaparsec. And the 1 parsec is equal to 3.1 into 10 power 16 meter. And of course, the megaparsec is equal to 3.1 into 22 meter. And the recession velocity, of course, it will be kilometer per second. And he started to find the speed by which the star is moving away from another object, or the galaxy is moving and expanding because of the motion of the galaxies and the star inside it. He found that as this distance increases, as the star moves further. So as further the galaxy is away from us, it will keep moving away from us faster and faster. And faster than another galaxy which is closer to us. I mean that if there is 2 galaxies, the first one is 1 megaparsec from us, and the second one is 3 megaparsec from us. You will imagine that these two will not moving by the same speed. The farther one will keep moving away, and each gaining of distance further from us, it will gain more velocity. And it will keep moving with higher velocity. And the universe started to expand, expand, expand. Then Hubble started to plot a graph, and he found that by putting the points between the galaxies, distance and velocity, it was a perfect straight line passing between all these points. So I mean that the relation between the recession velocity and the distance is directly proportional. And he said that V at the recession velocity is directly proportional with the distance between the stars. And of course, as we remove the proportional, we have to put a constant. The constant here is Hubble constant, H naught. And Hubble constant was, by dividing the recession velocity's value of the distance, H was all the time 72 kilometer per second mega per per second, all to the power -1, sorry. So by dividing this value over this value, it was 72 kilometer per second megaparsec to the power -1.
يعني second والميجا بيرسك كلهم -1 صح؟
No, 72 kilometer per second over megaparsec. So this is the value of recession velocity, and this is the value of the distance. Great. And he defined each node as Hubble constant. And from this relation, he states his rule, which saying that the recession speed v of a galaxy is directly proportional to the distance from it. Again, recession speed of a galaxy is directly proportional to the distance from it. And the mathematical
speed of galaxy ولا star?
a galaxy or even a star. But this one is for galaxies because after this point, he take this as an evidence that the universe expanded. And the universe is made up of galaxies. So the galaxies are moving further from each other. So it is about the stars, of course, the stellar emission, and it is for the galaxies too. So both of them. So V equals H node D. You don't have H node in this value. You have H node in SI value, as H node equals to velocity over distance, so it must be second to the power -1, right?
Yeah.
So we have to convert 72 kilometer per second megaparsec to the power -1 to second to the power -1. So first of all, we have to convert this value. So it will be 72,000 then divided by a value of 1 megaparsec, which is 3.1 into 10 to the power 22. Which give us the value of Hubble constant, but in SI units.
2.3.
Yes.
10 to the power -18.
Great. 2.3 into 10 to the power -18 second to the power -1. This is the value of Hubble constant. So we have how many constant even now? Do you remember?
Yeah. عندنا الهبل وعندنا السيجما صح؟
Yes. Stephen Boltzmann constant. And we have light year constant. Great. Then he used this prediction as an evidence that the universe started to expand. Because if you are looking at, this is Earth, this is two galaxies, and it seems that galaxy 1 is further from galaxy 2. So this is the distance D1, this is the distance D2. So it means that galaxy 1 moving away from us, which a velocity greater than galaxy 2, right? So
Yeah.
the universe expanding, and it will keep expanding till infinite. We don't know even now till what it will keep expand. But if we return it back, so we will reverse. This one was moving away from us by a higher velocity. And this one is moving away from us with a higher velocity, but lower than this velocity. So 1 million years before, maybe this galaxy was so close to us, and this one is away from us, right?
Yeah.
1 billion years before, this is the moment of Big Bang. So Hubble used his assumption in order to prove the theory of Big Bang, that if the universe is expanding away from us and the galaxies are moving and keeping stretching away by a velocity higher and higher, and as the distance increases, the velocity by which the galaxies move will be much more higher. So 1 billion years before, these galaxies was so close to the Earth, which means that it was the point at which the nature or the universe originates. And this called the time of creation. Then Hubble said that, so the age of universe if we have a relation, say that the velocity is equal to hd, and as d increases, so velocity increases. So if we reverse it as distance decreases, so the velocity decreases, it means that the age of the universe is approximately the reciprocal of Hubble constant. Because each distance away is multiplied by Hubble constant. So if we return it back, so as we decreasing the distance, so the velocity will decreases by reciprocal of Hubble. So when there was no distance, I mean that all the universe are closer to the Earth, it means that the age of universe approximately 1 over Hubble constant. If we calculate it, 1 over
0.3 10 to the power minus 18.
Yes. So it will give us
4.3 10 to the power 17.
So converting it into light years, into years also, sorry, for this one in seconds. So we need to convert it from second to year.
Divide 60 to minutes, then divide another 60 to hours, then divide بيطلع 1.38 into 10 to the power 10.
I mean 13.7 billion years.
يعني صح.
Yeah. So approximately according to Hubble's calculations, the moment of creation was 13.7 billion years before. So Hubble used his method to prove that the universe expanded. And as the universe expanded, it means that 13.7 billion years before, all the galaxies are closer to each other, and maybe they are condensed in one object. And this is the Big Bang theory. And this is the end of the astrophysics part. Here, you can open the mobile phone, or you can open the, to revise, if we cover all the points together.
Yeah.
I think I have a. Yes. Just give me 1 second. Where is screenshot? Yes. Okay. For Hubble's law and Big Bang theory, the candidate should be able to understand that the lines in the emission spectrum from distant objects show an increase in wavelengths. I think we covered this one. Use delta lambda over lambda, which is equivalent V over C. Of course, delta F over F it is the same, because the same value of changing in wavelengths is equal to the same value of changing in frequency. But this one will be positive and this one will be negative, because we will subtract the highest volume value of wavelengths from the lowest value, or the lowest value of frequency from the highest value. Is equivalent to V over C for the redshift of electromagnetic radiation from a source moving relative to an observer. Then point 3, explain why redshift leads to an idea that the universe is expanding. And I think we covered it too. And finally, recall and use Hubble's law V equivalent to H naught D and explain how this leads to the Big Bang theory. And I think we covered it too. And you have to know that candidate will only be required to use SI unit, but I mean that we will not use the value of Hubble constant in megaparsec. Do you have any doubt about this part?
Sir.
I think it is a new part. You didn't cover it even in O level or even advanced subsidiary, so it is completely new for you. But it is interesting.
Yeah.
Yes. And by the way, there is a specimen paper for 2022. And there is 3 questions about astrophysics.
Wow, 3 full question.
It's 3 parts in 1 question.
Yeah. 3 different questions.
No. 3 parts to cover standard candles and stellar radii and this one. Of course, we will not use any calculation for this part. We have only one rule, recession velocity equal h node multiplied by d. So it is easy. So I think if he asks about this part, he will ask about explain how Hubble used his method to prove the expansion of the universe or the theory of the Big Bang, something like that. Or explain how the line spectrum which observed from a star leads Hubble to discuss the meaning of the redshifting. I think the question on this part will be completely theoretical, because we have two methods of calculations for standard candles flux radiation intensity and for Stephen Boltzmann and Ven's law. So if he asked about a question problem, it would be even for standard candles and the rule of F and luminosity, or the two-step method of Stephen Boltzmann. While if he asked about this part, Hubble's and Big Bang, it would be completely theoretical. So any question about the astrophysics?
No, sir, no questions.
We will try to solve more because I said it is the first time, so I'm afraid about it, because we don't have any references. We have only some papers from Edexcel, from AQA, and a specimen paper. After finishing the chapter, we'll start to solve past papers, but these past papers will not be completed past papers. I mean that we will solve all the past papers from chapter 1 to chapter 5 at first, in order to be easy for you to revise. So from the beginning till ideal gases. After that, we will cover electric field and capacitor together. After that, we will cover the magnetic field and electromagnetic induction and alternative currents together. Then atomic, nuclear, and medical and ASTRO together, because they are related to each other.
Sir, and what about the oscillations?
I think it's canceled.
Really?
Oscillatory motion?
Yeah.
No. We will cover it. I said from chapter 1 to chapter 5. So gravitational, yes. So from chapter 1 till ideal gases, we will cover it in one session to solve
But ideal gases before the oscillation, I think.
Before the oscillation? No.
I think so.
Circular motion, then
Motion in circle, gravitational field, ideal gases, temperature, thermal properties, and then oscillation.
okay.
6 chapters.
Yeah, so we will cover the second chapter, this second chapter, till the electric fields and capacitor. Because electric field and capacitor are very, very difficult, and they have a lot of ideas which we need to discuss with each other. And if you have any other plan?
No, sir. No.
No. I will agree with you with any plan. So no problem. I just put this one because I didn't need to revise all the past paper together. We will just solve 1 or 2 paper in one session. While if we classified it into blocks, may we able to solve more than 5 sessions. May and June, October, November 2021 till 2018. If we cover this in one session, so it will be great.
For the first 6 chapters at first, right?
Yeah. At first 6th chapter, then 2 chapters, capacitor and electric fields together. Then magnetic field till alternative currents. Then from atomic till astrophysics.
سير and بالنسبة للشهر هذا بقى يحسن منهم صح؟ بعدين
Yes.
نبدأ بالشهر الجديد.
Yeah.
اوكي.
So we will complete discussing. If you have any doubt, so the next session, just send me all the doubts about the atomic physics till the astrophysics. If you have any doubts, so we can discuss it with us. Then we will start from the next month, inshallah, solving the past papers together. We will have also 3 sessions per week. We hope to finish at least from 2021 till 2010. So it will be great if we covered all these past papers. And by the way, we will solve it according to the marking scheme. So we will open the marking scheme and we will open the past paper, and each question we finished, we will correct it together.
Sir, I have some questions from some past papers. So can we start with them?
About which chapter?
I don't know, mixed. Because I used to solve past papers and see some questions. And then, like for example.
Okay, can you send it to me through WhatsApp?
Yeah. So just a second. Oh, yeah. Okay. صحيح برضه لأن MR طلع محذوف برضه.
ايه؟
ال NMRI طلع محذوف برضه.
Nuclear magnetic imaging reason؟ لا،
Yeah.
ما تزعلنيش، انا بحب
كتبوا band theory is removed برضه معاها ال NMRI.
البان ثيوري، بس احنا كده شرحنا البان ثيوري علشان خاطر نعرف نشتغل على اكس راي برودكشن.
So sir, السؤال الأول اللي مش حللهم.
Strontium is unstable nuclide. The activity of a sample is 1 × 10⁻⁹ kilogram of strontium 90 is 5.2 megabecquerel. Determine the decay constant lambda of strontium 90. Okay, let's start. He gave us strontium 90, so this is the molar mass. And activity A is equivalent to 1 × 10⁻⁹ kilogram per. No, this is a mass, right? So this is a mass.
Oh, yeah. Mass.
Okay. And the activity was 5.2 megabecquerel. 5.2 megabecquerel. And he need to define the lambda. Of course, we know that lambda is equivalent to A is equal to n lambda, right?
Yeah.
Okay. So lambda is equal to A over n. So we need to find n, or the number of undecayed nuclide, right?
Yeah.
N is equal to n, which is number of moles, multiplied by the mass. Sorry, Avogadro's number, right?
Mm.
We know that Avogadro's number is equal to 6.02 into 10 power 23. But how we can find number of moles? Number of moles is
Mass على molar mass.
great mass over molar mass. So I think it is easy. Mass is 1 into 10 power negative 9 kilogram divided by 90, which is the molar mass, multiplied by 6.02 into 10 power 23. So
لازم نحول كيلوغرام لجرام صح؟
is what?
Yeah.
No need.
Why?
It's yeah. It is in grams. But I think we converting the grams into kilograms.
So,
It is a molar mass per gram or per kilogram?
no, per gram, I think.
Yeah, it is about chemistry. Yeah, so.
Gram.
Yeah, okay. So it will be multiplied by 10 power 3.
Yeah, so it will be 10 to the power minus 6.
So the number of nuclei will equals to?
Even 6.7 into 10 to the power 15.
6.7 into 10 power?
15.
15, okay. Then lambda will equals to 5.2 into 10 power 6 over 6.7 into 10 power 15.
It lost 7.77 into 10 to the power minus 10.
Can you check the answer, please?
Yeah, I will do it.
Second to the power negative 1.
Oh, this is March. أنا دخلت على جون.
ايه؟
أنا دخلت على ورقة ثانية بالغلط على جون. هي مارش. Yes, exactly right.
Okay, great.
7.8 into 10 to the power minus 10.
Okay,
هي
great.
7.77 طلعت.
Yeah.
ما كنت عارف هاي الإيكويشن n
Yeah.
n into the
It is very, very important equation, by the way, because all the activity portions is just based on this one. If you are able to convert the mass and molar mass into number of undecayed nuclei, so it will be easy to solve any questions. And you will find it repeated in all past papers.
Okay, تمام.
Right. The next question. Electrons are accelerated through a potential difference of 15 kilovolts. The electrons collide with a metal target and a spectrum of X-ray is produced. Explain why a continuous spectrum of energies of X-ray photon is produced. Yeah, I think this is what we, if you remember the graph, the characteristics X-ray spectrum and the continuous spectrum. When we said, why this continuous spectrum? Because the difference of acceleration. Do you remember? This, we called it a continuous spectrum of X-rays, which give us all the energies levels. Because the difference of accelerations, because of the high potential difference applied between the cathode and the anode. So the electrons are bombarded by different velocities, which has different accelerations, which emitted from different energy levels. So they made a continuous spectrum.
Voice of Talib. Ah, okay.
So this is again the X-ray tube, and we said that we applying here between the target metal anode and the cathode a very high potential difference, which make the electrons ionization energy. So different electrons are started to bombarded according to their energy levels. So they have different speeds, which have different accelerations. So when it reaches to the target material, they have different energies. So a different photons will emitted. These different photons, all of them in one range, which is the range of X-ray, but with different energies. So we call it a continuous spectrum of X-ray.
Okay, so.
Can you check the mark scheme, please?
It says electrons decelerate on hitting target, so X-ray photons produced. This is the first mark. Then range of decelerations, one mark. Then photon energy depends on magnitude of deceleration.
Yes. So it depends on the accelerations of different acceleration values, as we said.
Oh.
Okay.
Yeah. Okay.
The last questions. The current in wire Q is less than current in wire P. State and explain whether the magnitude of the force on wire P is less than, equal, or greater than the magnitude of the force on wire Q. Great. Force. It is not a force per unit length. It is only force, right?
Yeah, force on the wire.
Right. So we know that F is equal to Bill. So if we have state and explain whether the magnitude of the force on wire P is less, equal, or greater than if the current, no, the current, so same force. F1 will equals to F2.
Why is that?
The force of the wire 1 is equal to B2I1L1, right?
Yeah.
And force 2 will equals to B1I2L2, right?
Yes.
we consider the two strength long wires are two parallel wires of same length, so they will cancel the length with each other. Because they are two parallel wires or two long parallel wires, so they consider them same length. So B2, which is mu I over 2 by D, right? Which I2 into I1 equals to mu I over 2 by D, which I1. So 2 by D was 2 by D, mu was mu I1 into I2 is equal to I1 into I2. So same force. So, and we can say it simply because of Newton's third law. According to Newton's third law, for every action, there is an equal but opposite reaction. So if the wire number 1 acted upon the wire number 2 by a force, so the wire number 2 must acted by the same force but in opposite direction.
Yeah.
So either you can say that because they were acted upon the same forces according to Newton's third law, or you can say that the same force because of the rule as F equal PIL and the same length, same P and same currents. Can you check the mark scheme, please?
Between force is the same. I will mark Newton's third law of motion.
Yeah, great.
Or force depends on the product of the two currents.
Yeah.
Exactly what you said.
Yeah. So this is very, very important question, by the way. All the three questions, because they are tricky questions. Thank you that you asked me about these questions. Because this is repeated questions and you will find it all the time. And if he wants to trick the students, he asked about these questions. Exactly, because all the other questions about calculation, so no problem about calculation. I think all the students miss marks because of the extended response answering questions, not because of the calculations.
Sir, I have other two questions, if possible, with you to answer.
Yeah, sure. Can you send it to me, please?
Yeah. سر أول سؤال الجراف بدي اللايت دامبنج فأنا حاله بس إنه أتأكد إذا رسمي صح ولا غلط.
Okay, just give me 1 second. Okay.
هو طالب باللايت دامبنج is this drawing right?
Yeah.
أنا رسمه.
Just give me a second to the depth of the bottle. The tube is placed vertically and then released. The variation with time t of the depth h is shown. Okay. So what happened for the amplitude? Decreases.
Light damping. Yeah.
So it stretched vertically or horizontally? It condensed. Vertically condensed, right?
Yeah.
Yeah, great. But you have to make sure that the beginning and the ending are the same peaks in the same places. Yeah, this point at 0.8 must be higher. I think it must be on the line, exactly. So it must be upward. But it's correct. But you have to, you see the blue line?
Yeah.
You have to complete to the end in order to make sure that all the points between the red and the black lines is matching together.
سير طب الاندنج صح لازم اخلص بنفس البوينت.
Yeah, sure. Because the frequency not changed. If you remember, we call the light damping from the condition of the light damping or the properties of light damping that they have the same frequency. So no change in frequency. Only the amplitude gradually decrease.
طب صار الستارتنج صح؟
Yes. Yeah. They will start at the same point by the same amplitude, but what happened exactly that after a period of time, it damped. And gradually damping by mean that the frequency is kept constant. Yes, Muhammad.
Sorry, what did you say again? إيش كيف أعدلها يعني?
You have to draw the blue line till the end.
Yeah.
And make sure that all the points which is lying on the blue line must match together.
يعني البلاك والريد على blue line at the same point.
Yes, exactly.
Okay.
Because it shifted at 0.8. Yeah, at 0.8, I think it's clear at 0.8. At 0.4 or 2. So you have to make sure that the blue line passed through black and red, and the black and red lying on each other exactly at the blue line. But the start and the end is correct.
Okay, sir.
Okay.
Yeah.
Which question?
الصفحة اللي بعدها هي بس بداية السؤال، أما السؤال هو آخر واحد. الصورة الثانية هي توضح أكثر، بس أنا صورت لك من البداية صح؟
Yes. He said that the small coil has an area of cross-section 7 into 10 power negative 4 meters squared and contains 75 turns of wires. A constant current in the solenoid مش باينة page 18 of 28, but we will try to read. Solenoid products a uniform magnetic flux of flux density. The direction of the current in the solenoid is reversed in a time of 0.12 seconds. Calculate the average EMF induced in the small coil. Okay, EMF induced is equal to delta I over delta Z, right?
Yeah.
Okay, so EMF induced is equal to delta I over delta T. Of course, if we have number of turns, so we will multiply it by number of turns. Okay, which equivalent to N delta phi over delta T, right?
Yeah.
And the phi, of course, is equivalent to delta P into A over delta T. Right?
Yes.
So we have the cross-sectional area and we have the number of turns, a constant current in the solenoid. Constant current, the direction of the current in the solenoid is reversed. I think it is 0. Constant current, not a changeable current. So delta I over delta T is equivalent to N delta P A over delta T delta Q, yes. So delta Q over delta T. We cancel this one. So delta I is equal to N delta PA, right?
Yeah.
Okay, we have N, which is 75, multiplied by P. The changing happened in P. Did you calculate B before?
They told produces an electromagnetic flux of flux density 1.4 milli T. Just
Okay, 1.4 into 10 power negative 3, right?
Yeah.
Okay, so this 1.4 into 10 power negative 3 multiplied by the area. The area is 7 into 10 power negative 4.
Yeah.
Okay. So this is delta R. Then divided it by delta T, which is 0.12 second. It will give us the EMF.
It's about 6.125 into 10 to the power minus 4.
Okay, can check the mark scheme.
So the mark scheme, it says 1.2 into 10 to the power minus 3.
1.2 into 10 power negative 3.
Yeah.
Okay, 75. Small coil. Okay, this is a small wire. We need the large wire. The large wire contain how many turns?
What's mean? It's mean.
What?
مش كاتبين sir.
Delta I equal N delta P. So delta P change it. This is constant. So the small coil had an area of 7 into 10 power negative 4 and contains 75 turns of wire. Constant current in solenoid is passing and form flux density of through the small coil. So this is P of the coil. The direction of the current is inverse to 0.12 induced the small coil. Again, EMF equals to delta I over delta T. And the change happened in current is equal to the changing happened in flux multiplied by the area multiplied by the number of turns in, correct?
Yeah.
Okay, the number of turns 75 and the cross-sectional area is 7 into 10 power negative 4. Yeah, we need to find the changing happened in flux. So delta B is equivalent to what? According to I, so mu I over, this is a solenoid, right? Mu I over mu n I, so P mu n I over L. We don't have the radius.
No.
We have a radius.
لا بس ممكن إنه area equal pi r square صح؟
Okay, so area is equivalent to pi r squared, but this is the radius of the coil, not the circle. So this is for the coil. Okay, great. So R is equivalent to the root square of area over pi. So the root square of 7 into 10 power negative 4 divided by pi, equivalent to
0.015.
0.015. Okay, we need to find the length of the solenoid. So the length of the solenoid is equivalent to the perimeter 2 pi r multiplied by the number of turns, right?
Yeah.
But this one, okay, will be cancelled with this one. So P will equivalent to mu I n over 2 pi r n. So n will be cancelled with n, right?
Yeah.
Okay. Cross multiplication. So I will equivalent to 2 pi rp over mu. So can you calculate the current?
يصير البي استعمل 1.4.
Yeah, 1.4 into.
يصير ايش كان الميو؟
4 pi into 10 power negative 7.
مية وأربعة. نفس السؤال. قصدي ايش؟
Okay.
104.3.
104.3.
Yes.
Okay, divided by the time. The time is 0.12.
0.1. Yeah.
So it will give us
869.
what?
869.
869? No. 104.3 divided by 0.12. So multiplied by 100. Okay, can you check the mark scheme?
Okay. صار بعثت لك ايش كاتبين.
Yeah.
Part C.
Let's see. Yeah, so the same. But how this is what we solved at the first.
So they multiplied it by 2. Look, the number of terms into BA, then times 2.
75 is the number of terms. Multiplied
Yeah.
by 1.4 into 10 power negative 3, which
Yeah,
is
this is
the
the
flux, right?
Yeah.
And
Yeah.
7 into 10 power negative 4, this is the area, right?
Yeah.
Yeah, the area is multiplied by 2, yes.
Why though?
Yeah, because we have 2 coils. Back to the question.
Talking about the small coil only.
He said that. Yes, yes. The small coil has an area of cross-section 7.10 to the power negative 4, right? And what is the area of the largest one? It is doubled, right?
Oh no, ma, he didn't give us any information about that. So maybe with the reversed word, the direction of the current in the solenoid is reversed in a time of 0.12. Maybe it's related to this.
Reversible mean here the change, the variation, in order to make electromagnetic induction. But the area is multiplied by 2. Yeah, the area multiplied by 2 because we have 2 coils. I think the coil, the larger coil, is double the area of the small coil. Can you read the question from the beginning? Small coil is connected to the excess pressurized current induced. Small coil, this induced current give into amplitude field, steadily slow. Okay, we can. Solenoid is connected with the battery is illustrated. How many terms here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8. No, I think the area is doubled. And this is why we are using the area of the larger one. Which is this one? May and June 2019, right?
Yeah. Table 41.
Yes. Yeah, I know the answer. Yes, yes. Yeah, when the current is reversed, it is passed through the coil twice. Yes. When the current is reversed, he passed at the first time, then he returned it back to pass through, so it passed through double the area. Yes. That's why he put here 2. So n delta phi over delta t is the same equation, but the word here, the current reversed. Yeah, good question. The current reversed, the direction of the current reversed in a time of 0.12, so it passed twice. So it passed twice the area, so we have to multiply the area by 2. Yes, great. Muhammad?
Yes, sir.
So the area is doubled because the current passes through the coil twice.
Okay.
Do you have any other question?
No, sir.
Yeah, but this one is a good question too. Okay. We have a session on Thursday, inshallah.
Yeah.
This session will be all the questions that you have a doubt about. If you need to discuss any part of a chapter before we start the revision and past paper solving from the next week, inshallah.
Okay, sir. Tamam.
Inshallah. I'm waiting for your questions. And if you have any parts you need to cover, just inform me on Wednesday. We have tomorrow, Wednesday, yeah?
Yes.
You can inform me tomorrow, inshallah, in order to prepare all the parts.
All right, sir. Thanks.
Okay. See you on Thursday, inshallah. Do you have any other questions?
Thank you
Okay.
so much.
Yeah.
Yeah.
Good night.
Yes,
See
Good
you.
night, sir.
Yeah.
See you.
Bye.
Bye, sir.